Yeah, we're live now. So, hello and namaste, everyone. Welcome to the Online Space Workshop 2020, jointly organized by AMSAT Nepal and Orion Space. I am Saurabh Paudel, your host for session first. With me today, we have Mr. Abhas Maskey as a speaker and Mr. Jiten Thapa as a participant. Mr. Maskey is the project manager of Birds 3 satellite network, through which the first satellite of Nepal, NepalSat 1, was launched. Mr. Maskey's interest is on camera designs and currently researches on machine learning for CubeSat imaging system. Today, he'll be presenting about the basic of camera design for low Earth orbit Earth observation. If you have any queries, you can write in the comment section in our YouTube live, and our colleague Jitan Thapa will be sharing the questions into the meeting here, and Mr. Maske will try to answer your questions. So for now, I'd like to hand over the session to Mr. Maske. So here to you.
Okay, thank you, Saurav. As Saurav said, I'm Abhas Maskey, currently the project manager for Birds 3, and I am a PhD student here at Kyushu Institute of Technology. And today I'll be presenting about how to build a camera from scratch and take images from low Earth orbit. Okay, so basically what we're trying to do is remote sensing. First of all, I would like to introduce what CubeSats are, just in case that you don't know. And then I'll introduce you to some projects that we are doing in QTech. I'll also introduce you to imaging, and then we'll go through the design process and look at some of the results. CubeSats are basically a standard. These are standards for nanosatellites, anywhere between 1 to 10 kilo class. 1U, which is the smallest standard, is defined as 10 by 10 by 10 centimeter, weighs about a kilo, and are single watt. So we call it swap requirements. Okay, so these are single watt, very small, 1 kilo. You can fit in your hand, as big as Rubik's Cube. I'll point it out to you here. And if you need more power or if you need more volume, you can just scale that up. This is a 3U. If you look at the trends in CubeSat, we can see that there is an exponential rise. I know you've been looking at these kind of exponential graphs these days quite lately with coronavirus, but this one is with CubeSats. You can see that the number of satellites being launched every year is exponentially increasing. This is not sustainable in any ways because at some point it will saturate, and we'll probably see a lot of debris in space, but there are debris mitigation work that's being done. All we want to see here is that the CubeSat trend is increasing year by year. QTech ranks #1 in all small satellite launches for academic and nonprofit organizations. As you can see here, we have launched so far 16 satellites. We have a number of CubeSat projects and small satellite projects that are going on. We have an excellent center for nanosatellite testing. We can test space environment, rocket environment, and also we can do anechoic chamber testing. So far, we have tested all these satellites in Kyushu Institute of Technology. We have the capacity to test anywhere between 1 to 50 kilo class. Bird Satellite Project is a project that we are doing right now in QTech, in Kyushu Institute of Technology. It's an acronym for Joint Global Multinational Birds Satellite Project. It targets non-spacefaring countries. And basically, the idea is to build, test, launch, and operate satellite in 2 years. 2 years because a master's degree student could be 2 years, right? So we want to start when he starts his master's and then finish when he or she finishes his or her master's. So far, we have gone through Birds 1, Birds 2, Birds 3. I'm involved in Birds 3. We have also Birds 4, where we have Hari Ram Shrestha involved. And then we have Birds 5, which kicked off recently. But due to coronavirus, we are not sure how that's going to go forward. It's a worldwide recognized project. We have won a number of awards, including the GDC Airbus Award in 2017, and we won the Better Satellite Award, World Award in 2019, alongside UK Space Agency and Geek Without Frontiers. Currently, we are also involved in the Kitsune project, which is a 6U project. It has a high resolution imager, and then also a small camera. So this one, all the birds countries who are involved are also involved in the Kitsune project. So that's the projects for Kyushu Institute of Technology. And today's end goal will be to try to take an image from space. Okay, so what does it take? How do we think about designing? What's the process involved in going from start to finish to be able to take an image like this? Okay, let's move on to imaging. So what we're trying to do basically is when we take out our phone and take off image, we are remotely sensing that information. There are two types of remote sensing data. You have the actively sensed data, and then you have the passively sensed data. Passive sensors are basically capturing the reflection, some reflection. Okay, so light comes to an object and then reflects back. What we are talking today is on the RGB spectrum, which is the visible spectrum, red, green, and blue. And these are some of the images taken by CubeSats. Visible spectrum lies, as I remember, for 400 to 700 nanometers. This is the spectrum that our eyes are sensitive to. And to represent light in digital form, we need some kind of sensor, and that's done by an image sensor. This is an example of an image sensor with filter and everything. If you take off the filter, you can see that the actual image sensor is here, and then you have all these connections. These are a packaging, and this one is a special type of packaging called PLCC package. So the way you would, the way you would connect these points to a PCB is through soldering. Okay, so that's how you access the image sensor. So what we do is we have to digitally represent the light that's being reflected, and we need to capture red, green, and blue. If we mix all these colors, then we can represent any color. To do that, what we're doing with the phone is we can only see one sensor, but we need to capture RGB. So what we do is we put a Bayer filter. It's already built into the image sensor. It's an external filter. So the R allows only the red light to get in, G allows only the green light, and blue allows only the blue light. Because our eyes are sensitive to green, we have doubled that. The number of pixels that represent green are more, and red and blue are less. This is how the pixel is sensitive to light. So you can see the same image sensor is sensitive to blue, green, and red. And if we just want the red, what we do is we put a filter and we cut off the rest of it, and we only receive this. So only red is being represented. There are also other methods, not just using a Bayer filter. So you have a light, and then we do beam splitting. This is technologically a little difficult to do, but we have three images that only gets red, green, and blue. Instead of that, we can use three cameras, like how DJI is doing it here. And we can see number 3 is for green, number 6 is for blue, and number 5 is for red. But just because we put the sensor out like this doesn't mean we'll capture the light. We need to focus the light onto the plane. To do that, we need to have a lens. Okay, so that's where optics comes into play. We need an optics to then focus the light onto the sensor. And what I want you to remember here is two things. One is the focal length, another one is the field of view. And what we'll be dealing most is the focal length here. So if you reduce the focal length, you can see that the field of view increases. So there is some kind of relation between focal length and field of view. Okay, so I want you to remember that. Now we're talking about the module. You have the PCB, the image sensor, then you have some kind of holder that holds the lens, and then we have the lens. So there are different types of image modules. This one is the one that's inside a Pixel 3a phone. Just using the module, unfortunately, is not enough. We need some kind of external controller. This image sensor could have a system on chip itself. It could be intelligent itself, but there needs to be some other controller that allows it to understand what kind of image to take. Okay, so this image module is being then connected to then expanded module, which has an image controller and some memory because it needs some running memory, and then it exits some image. These are some of the things that I've worked with before. In my undergraduate degree, I tried to hack into a GoPro camera, use a camera controller, and then control the GoPro. We put that into test in a CanSat, in Korea CanSat competition in 2014, and we were able to get these results. For SnooSat 1B, I was also responsible for designing the camera. This was my first design. So you'll see here that there is an image sensor, you have the lens, you have the lens mount, you have the camera controller here with an STM processor. But because of the volume requirements, we had to change the design again. We needed much more vertical design, and we came up with this. And it's also used for SnooSat 2 project. This was designed in SolidWorks. In some cases, you might not even need a structure to hold the lens. You have the lens holder here itself, but not an external structure. In case of Birds 3, we did that because we used a backplane board. We make PCBs and then we mount them on this PCB, and then that PCB is mounted onto the structure. You'll notice there is an image module, controller, and memory. With Kitsune, we are currently working on a 5-meter resolution imagery. For that, it's more complicated than just taking an image. We have to be careful about thermal situation because thermal expansion would then change the lens, the focal length, and we need a specialized holder. So this one is for Kitsune. It's much more bigger. We're trying to fit that into a 3U. This one is a 6U, but the camera will be 3U. So let's now look at the design process. Some vocabulary to understand. We'll look at temporal resolution. Temporal resolution is basically how many times does a satellite visit the same place in one day. Okay, so that's temporal resolution. Spatial resolution is the area covered. If you're talking about ground sampling distance, it's the area covered by 1 pixel. If you're talking about ground swath, it's the area covered by the whole image sensor. Okay, so you need to find the difference between this. So I hope you have understood that. We have to also think about orbits, what kind of orbits, because that actually affects the resolution. And then we have the pixel size. Pixel size also affects the resolution. And then we have the focal length, okay, focal length. So let's suppose that we set a requirement. And somebody asks us to build a satellite that takes an image of entire Nepal once a day. Entire Nepal shows an area, so that means we're talking about ground swath. In case of another requirement where we say, I need a satellite that takes an image which is less than 5-meter resolution in any given day. Then we're talking about ground sampling distance, GSD, okay, this 5-meter resolution. So just to give you a sense of what 5-meter resolution looks like, let's have a look at Pokhara International Airport. Now, this is being built currently. And let's say this is especially useful when if the government is saying 80% is done, we can use satellites to verify that and see if that's really 80% or not. Okay, so 5-meter resolution data gives you this kind of information, which is very useful. So normally you choose between ground sampling distance and ground swath. Okay, so either one of them. So this is Kathmandu University. I haven't been to Kathmandu University for a while now, so I just tried to see if any changes are being done. And if I'm not wrong, I noticed that there is a swimming pool at this moment. So 5-meter resolution gives you quite some information. Now let's look at the orbits. We said that we need a 5-meter resolution image once a day. Okay, so once a day. In low Earth orbit, we can choose between sun-synchronous. These are just examples. Sun-synchronous orbits and international space orbits. So let's say we have to choose between them two. So polar orbits or sun-synchronous orbits, empirically speaking, through experience, I know that there is 2 good operations per day, at least. And with ISS, International Space Station, we have 4 good operations per day. So let's say we choose International Space Station orbit, okay? So that's about, it varies from time to time, but let's say average 400 kilometer. And we want to take a ground sampling distance of 5 meter. We use simpler trigonometry to be able to calculate what pixel size sensor we need and what focal length it should be. However, as you can see here, we have 2 unknowns. Okay, there should be only 1 unknown. So how do we even solve this problem? How do we know what sensor to select, what focal length to do? The idea about using CubeSats is that we're trying to use commercial off-the-shelf components. Basically, what that means is any components that is available in the market, not specially designed for CubeSats. We'll have to look at all these lenses, and we do an extensive market study. So step number 3 would be to actually look at market and understand and see and find what kind of sensors and what kind of lens is available. Okay, so you list them out, and then you reverse calculate the ground sampling distance. We know it's 5 meter, or 5 meter or less is good. So let's suppose we found a image sensor with pixel size 2.4 micrometers. You put 2.4 micrometers here. And then the lens, the focal length of the lens that you have selected is 300 millimeter. Then you put the focal length here, and orbit height is around 400 kilometer. And then you make sure that the units are consistent, meter. So you'll get around 3.2 ground sampling distance. If you do it mathematically, you will see that too, 2.4 times 400 divided by 300. So it's around 3.2. I think this is what a lot of CubeSat teams miss out on. We have to build a requirement allocation sheet. Obviously, a lot of CubeSats have requirements, but they don't put it in a requirement sheet. So it's very important to do this because other people can also actually see. So the question we are trying to ask here is, how are we going to test the camera? So now that we have selected a sensor and lens, right? How do we test it? What is the maximum power energy consumption? Very important aspect. What is the volume? Maximum volume that we can allocate. What about the weight? What about space thermal? There could be thermal expansion. What about radiation outgassing? But I think the most important of all is the data. How much data can we take? Because to be really honest, the bottleneck is not on the image sensor. You can put any megapixel up in space. But if you cannot downlink that data, there's no point. So if you're using a UHF amateur radio at 4.8 kilobits per second, And if you dedicate all the energy, you get 700 kilobytes of data per orbit. Okay, so 700 kilobytes of data. But what we have seen practically is we only get about 1 to 5% of the data itself. And there are certain reasons for that. I'll explain it later. So to reduce the image size, what we can do is change from RAW to JPEG, which is software. We use compression algorithms. We can also use thumbnail. So from a bigger resolution image, we can create a thumbnail like this. So we don't lose any field of view. We can then create a image. We can also cut or crop images and reduce the size if it's necessary. Okay, so since we have talked about requirement now, let's start with the sensor because that's where everything begins. One thing you could do with sensors is buy the sensor and then build a module. Okay, so you put the sensor onto the PCB. So this is what I did initially, and I think this is good for research purpose, but there are a couple of problems. One thing is the datasheet could not be available. Another one is you have to create the library yourself, and it could be unstable. So you have to really think about the software support. Okay, designing a hardware isn't the biggest issue. I think the biggest issue will be on the software itself. So if you're doing research, it's okay to do this. But if you're doing CubeSat team, it's better to look at an image module that has plenty of support and is open source and has software developed already. So then you can start playing with that. And I would suggest to buy a module in that case. So after you have a image sensor module, then you need a microcontroller and you also need a flash memory. I would suggest to use a microcontroller with a image interface. So some of the microcontrollers might not have image interface. STM has a thing called DCMI, digital camera interface. That allows it to directly connect to the camera itself and get the data out. PIC controllers don't have it, so it's a bit complicated. So once you have actually selected other components, which is step number 5, you need to go to step number 6, which is basically, sorry, this is step number 5, right? So step number 6, right? So we need to create a block diagram, okay? So you need to know how each component is connected to one another, all right? So you have the camera module here, and then you have the MCU. How is the MCU connected? What interfaces are we using? So this is for the birds 3, but you also have to understand how it's connected to the other systems. How is it connected to the OBC? How is it connected to the communication? How is it going to be downlinked? So these are something that you have to really think about initially. This is another example for Kitsune. Unfortunately, I cannot show you what's inside, but this is just an example. So it does get quite complicated as the systems evolve. To solve this problem, what we do is we create a interface control document, and this is extremely important. I think I cannot stress how important this is. It basically shows how the camera is connected to the other subsystems, okay? So if you get this wrong, that the whole system could collapse. So once you have that done and you know how it's connected and you have made the block diagrams, what you need to do is then start physically working on the camera. So far you've just selected components and drawn block diagrams and so forth. So the whole point of breadboard models is to create a system level proof of concept. First one is to use a actual breadboard. So you have all these wires that goes into the sensors, and then you try to communicate. I think another better way is to use a development board. So if you can find a development board for your MCU and also your module, then that's even better. Another way is actually, this should be number three. I apologize. Number three is soldered BBM, and this is something that you can also make. Makes life also easier, but there's also chance for mistakes. You can also go forward if you know how to design PCBs to make a PCB BBM. This makes life much more easier, but you need to know how to design PCBs beforehand. If you're starting out, I think act- building an actual breadboard model would be better because you can just take off wires if necessary. Okay, so once you build a breadboard model, now you need to start designing the software. So you have the sensor library software, you have the flash memory software, for example, library, and then you have the core code, which is the actual algorithm that's been implemented on the camera. And then you need some kind of low-level library to support this, okay? So let's say one of the mission modes is taking snapshot. To take a snapshot, we turn on the camera, we initialize peripherals, which is basically I2C, UART, whatever. And then we wait for the command from OBC, let's say. And then the command comes, we complete a handshake basically saying that, hey, I'm alive, I'm okay. And then we initialize the camera module, we check the SPI and I2C with the image sensor. We send a command to take an image, and then once it takes an image, we compress it to JPEG and then store and send the image back. Okay, so this is basically how to take a snapshot, just an example. So once you know how to take an image and software works, you start testing. You try to represent the color, see how it's distorted because of the lens. If you use a wider focal view, FOV lens, then you get these kind of distortion. It's called a barrel distortion. Once you have that done, then you want to actually work on building the engineering model. Okay, so now that you had the block diagram and that you have represented it in physical form and you know it works because it took a photo, you now start working on the schematics. I use Eagle. Before I used to use pads. Eagle gives 3-year free access for students, so that's nice. This one is the design for Birds 3 camera board. As you can see here, this is where I think until schematics it's fine, you just connect, but layout is where you have to be extremely careful. How do you place oscillators? You can see here that it's symmetrical. You have the load capacitors here, the oscillator, and the way the traces are going. These are very important things. You'll also notice that no traces are going underneath oscillators. So this is just to comply with EMI conditions, right? So you want to be careful how you design it. Um, this was a 6-layer PCB. If you just look at the third layer, we can see that how the power is being supplied to other subsystems inside the PCB itself. So you build an engineering model, and then you give it for manufacturing, and then you solder it. Once you solder, you start testing it. And before you test, you integrate it into the subsystem now. So this, I think, probably the most important step of all is integration and testing. And this will take, people always think this will take, let's say, if they think it will take a week, it will probably take a month. Integration is something like that. So it will take some time. So for testing, because we are in low Earth orbit, we do have certain radiation there, especially the South Atlantic anomaly that creates high doses of radiation, active particles. So what we do is we do a radiation test. We can do total ionizing dose. By experience, I've seen that it's really not necessary unless you just put it for orbit for 8 years. If it's 2 years or 1 year or lifetime, I think it's still okay. Integration, after integration, you have the testing, the vibration testing. The vibration testing is You can do subsystem level. This was done for my master's degree. But normally you just don't have to do that. You just integrate it into a whole system and test them. So not only are you going to test your camera, you're going to test the whole system as well. So vibration testing is necessary because of the rocket environment. So rocket induces certain vibration, and that is induced on the satellite. You want to see if any components gets off or not. Okay. We also want to test on a thermal vacuum chamber. A thermal vacuum chamber looks something like this. This is the small chamber that we have. We also have the big chamber where we can fit multiple satellites. You'll notice the camera is here, and we were testing it from minus 45 degrees Celsius to 55 degrees Celsius. So we did 4 cycles. So we let it cool down, and then we do a cold start. So the satellite starts, and then we start heating it up. 1, 2, 3, fourth cycle. And in fourth cycle, we take it to an extreme level and see if the satellite is still functioning and the camera is still functioning. And we can look at the data here. This is what the camera was measuring inside. The lowest temperature that we were able to go to was minus 15 degrees Celsius. Okay, so and it was still working, and the highest was about 68 degrees Celsius. And just to let you know, this is just not thermal, but this is also vacuum. So it's a thermal vacuum chamber. So this has been tested in a vacuum condition. So once you have the engineering model done, you improve slightly on the verified model, and then you give it for manufacturing, and then you integrate them together. Okay, so this is how we integrated them. Extremely careful. This is probably the most difficult step and time-consuming step, where you'll have to be extremely careful not to drop anything on the solar panels. It might break on the camera itself. If you upload the wrong software, there's okay, so everything that you have worked on will go into the dustbin. So you have to be really careful here. So we integrate, and then we test again. Engineering models are tested in, we call it qualification level, so higher levels of testing. But for flight model, we tone it down a bit. So we do it acceptance testing. So we don't induce too much of the vibration or thermal vacuum onto the flight model, because we think that could create some engineering fatigue. And after that's done, we let it run for a significant amount of time just to see if there is any software bugs. We conduct the mission as if it's in orbit. We send commands, and the satellite receives the command, and it takes an image, right? And that's called a long duration test. After we do that, we deliver the satellite to the launch provider. The launch provider then launches it, and then in Birds 3 case, we deployed it from International Space Station, but others could actually use rockets. If you're using rockets, then you have to also do shock testing. If you're deploying it from ISS, you don't need to do shock testing. Now let's have a look at the results. Okay. Let's say the satellite is in space now. What happens is we want to take an image, and we send a command from the ground station. And from the ground station, the command goes up. The satellite's antenna receives it, transmits it to the communication module. The communication module transmits it to the communication controller, then goes to the onboard computer. the onboard computer knows what command it is, and then asks the camera MCU, which is the controller, to take an image, then sends a command here. The image sensor then takes an image, sends it back, and sends it and stores it on the flash memory, which is the common flash memory. Another thing to think about design is redundancy. Okay, so what we have done here is we have placed two camera flash memories. When it's storing here, it's also storing here. So just in case this SPI breaks down, we can then use the UR to access this image. Okay, so there could be a case where this flash memory dies or SPI breaks, then we still have another way of accessing the data. So this is built into the design itself. And if you're talking about, let's say, robotics on land, you don't put these kind of redundancies, too much redundancies, but with space, you have to make sure you have put it. So that's taking image. Receiving image, well, you send another command, and at this point, the main onboard computer has already taken that image and stored it onto the local flash memory of the communication PIC, which is the controller. The command comes in, and then the COM PIC understands the command, then takes the image and sends it back down to the ground station, and that's where we receive it. In the first 90 days, first 90 days of operation, which is 3 months, we were able to collect 30 images. So in that rate, we can see we are collecting 2 to 3 every image 2 to 3 days. Okay, so we have been able to take Sri Lanka, Mongolia, Nepal, Bhutan, Bangladesh, and all these images. Even South Korea recently. We have taken Japan, Kyushu, which is the place that I'm living in right now, and we release these images every week. The satellites are still operational. We expect them to operate for another 14 months, empirically speaking, and all of these data are being uploaded on the BIRDS project. Okay. So to conclude, what we did today is introduced CubeSats. What are CubeSats? And we understood that they have certain limitations. We looked at some of the projects that QTech is doing. We went through the entire design process, from selecting an image sensor to designing the PCB to taking an image. And the same process actually can be applied to other systems. I've built onboard computers, I've built EPS systems. I use the same process, and results are based on process. So if your process is good, the results are good too. So again, the focus has to be on the process, and you have to also think of engineering trade-offs. One extreme engineering thing that I recently saw was using Mi 10 phone on a CubeSat. They have 108 megapixels. I think it took a lot of time to be able to downlink this image. So they put basically a phone and took an image like this. This is a Chinese satellite. Thank you.
Thank you for the presentation. So we have a question from our audience. The question is from Ricardo Arturo. So we have also shared the question in the group chat as well. So the question is, how can you take off the freezing on lenses in space? And how can you control the internal pressure in the barrel lenses?
So normally, what we have seen empirically is that we haven't seen any freezing of lens so far. And even if that's the case, what we do is, let's say, in worst case scenarios, we place heaters So to tackle, let's say in a worst case place that there is really a freezing event happening, which we have not seen so far. Um, we put heaters on we wrap the lens with heaters. They have temperature sensors. So every time it goes below certain amount of temperature, then the heaters turn on and the temperature is maintained. Okay. What was the second question?
And how you can control the internal pressure in the barrel lenses?
So basically, if you can control the temperature, the pressure is also controlled. And on top of that, what we do is we do a massive amount of testing first. It's not that we just send it up to space. First is a lot of testing here in the ground in vacuum conditions. And what we've seen is these kind of M12 lenses can withstand that kind of pressure. So no problem so far.
Okay. So I think that was the question from. Okay. So there's another question: which program is used for camera and also the overall CANSAT? So that was the
Um,
question from
yeah, so
Aryan Hab.
software wise, what we can do is most of the library is written in C, of course. But then I've actually come across this new camera. I forgot the name, but they're using MicroPython. So you can program in C, you can use MicroPython. If you're using Arduino, I do know that you can use C++. So depends on what kind of module you're using, but most of the library that I've seen and people have built, let's say, let's go to the software part. Where did I put the software? Blah, blah, blah. So anyways, yeah, so in if you're thinking about the software itself, most of the library is being designed on C. Okay, yeah. I hope I answered that question.
Okay. So I have my personal one question from myself. So what was your challenge while designing a camera for Nepal Sat 1? Your challenge while designing the camera mission for Nepal Sat 1?
I think people underestimate the amount of time. It wasn't a challenge specifically for me because I already faced that in SnooSat. I had I think if you ask me what challenge was there when I was designing camera for SnooSat, I'll tell you a lot of problems.
Okay.
But because I had that pre-experience of designing cameras before, and my master's and undergraduate was on designing camera from scratch,
Hmm.
that wasn't a big problem. But what I see time and again with other people, at least, is that they underestimate the time it takes to. You can design an image, right? You can image sensor. You can create a module. You can take an image, but they underestimate the time it takes for it to be integrated into the system. So, let's say you send us the satellite into space. Even if it works one or two times, doesn't mean the camera will work all the time. It has to be working 100% all the time. Every time you send a command, will it work or not? I think that's something that you need to test, right? So the biggest challenge, if I have to directly answer your question, is to make sure that the image sensor will work 100% of the time every time the command comes. I think that's the biggest challenge. It can work one or two times, but so far we have seen 100% success with the camera.
So you mean so we have to test for the long duration testing, right?
Yeah, I think it's you have to test long duration. There is
Okay.
no other option.
So one more question. So what's your plan after completing a PhD?
A plan. Okay, so the point of BIRD's program. Let me go back to that slide. Bum, bum, bum. There should be a faster way to go back. So the point of this BIRDS program is to train people from countries which don't have a space program, right? So we did build our first satellite for Nepal with BIRDS 3.
Mm-hmm.
The point is to train engineers and then send them back. So I've been requested to go back, which I will do. So I'll come back to Nepal. But because of the coronavirus situation, all the things that we had planned and all the timeline we had made right now is uncertain. So I cannot say anything at this moment in time, but what I can say is I'll be back in Nepal.
So one more question. So do you route the PCBs in Eagle with auto router or you route it yourself?
Very good
So
question.
also
So
there are two crystals in STM32 microcontroller. One is for high frequency and one is for low frequency. So what are the differences on it? So why there are two different frequencies used in those microcontrollers?
you mean the frequency in which you run the microcontroller?
Yeah, exactly. The
Okay, so
oscillating frequency.
well, so frequency directly relates to the power consumption. So if you lower down the frequency, you consume less power. If you higher the frequency, then you use more power. If you need to have real time, really quickly data, then you need to increase the frequency. So that's the only thing I see. Okay. So if you really need the data real time, immediately, it needs to be processed quickly, then you need higher frequency. And especially with images, you're just dealing with matrices. So actually, if you have a GPU system, it parallelly processes it, right? But MCU is just one thread, single thread. So you need higher frequency to calculate it faster. I think that's the case. And also, I think STM32s have floating point units, which is very good. I think that's and if you have a higher frequency with MCUs, you can use FPUs, yeah, as well. So in case of Eagle, um, in SNUSAT, I used to do auto route with pads. With Eagle, I do hand route. Everything is hand route. No auto route at all. So it takes incredible amount of time.
So is there
But
any specific reason like
okay,
choosing for?
right. So if you do auto route, what I've seen is you don't find problems. So if I do hand route, what I see is I route from one place to another, and I start observing that there is some error in schematics. And what I've noticed with auto routes is that you sort of miss that. You can get it correct. Like I don't think there is any specific problems, but you can have more control if you're doing manual routes. You can also make sure that nothing is going under the oscillators. You can put design rules, but design rules can only help you in a limited amount of time. But what I've seen with people who are much better experienced with PCB design, and when I took those courses, was they use mix. They first route the most important lines in the way they want, and then the lesser unimportant are auto routed. So you can use mix as well.
Okay, so we have one more question from the audience. So it's from Kopilik. So his question is, which image format do you recommend for transmission? I mean JPG format or BMP format, and how to calculate the error in packet loss?
Yeah. So what we do is we use JPEG. JPEG is the standard. I try to study that too, what format other people use. JPEG seems to be the standard. Error correction is not, okay, so error correction is not down here in the ground. Error correction is in the space. So the way you would do that is you send the file, and then there is another, let's say OBC or COM, which makes sure that whatever packets it's creating is creating correctly. So the algorithm is there to check there itself. And whatever is being sent here, unless we miss a packet, that's another question. But whatever packets we have received so far, all of them have been correct because there is an error correction, packet correction code implemented on the communication PIC or the MCU or the controller in space itself.
So his question was also about the packet loss. So how to calculate the packet loss?
So we have seen, um, empirically speaking, we have seen packet loss. That's a very good question, actually. 5 to 15% packet losses. Yeah, so 5 to 15%. So let's say we are downloading an image. We see that certain part of the image is missing, so we have to download it again, right? So we see that 5 to 10% or 15% of the time. And the reason why that happens is probably because the antenna is not being calibrated properly. So, or there is some kind of interference, like some kind of weather condition that creates that kind of system. So every time we have, let's say, initially we could have 0 packet loss, goes to 5%, goes to 10%. Then we calibrate the antenna to azimuth again. And once we calibrate that, we reduce the packet loss.
Okay, so I have one more question. So, how many packets was the image from Nepal Sat 1 or the Burst network was divided into?
So it depends again. Eh? So if it was raw, you know exactly how much images. The size. Okay. So
Mhm.
let me go down. But in case of JPEG, in case of JPEG, you can see that the size is anywhere between 77 to 73 kilobytes.
Mhm.
Okay. And we downlink about 2 to 3 days per image. So looking at that, per day we downlink about 12 kilobytes to anywhere between 35 kilobytes. So looking at that again, the number of packets will be 7 times, let's say maximum we have reached is 7 times 50 packets. So that's 350 packets maximum.
Okay, so you talk about the packet loss in last question. So my another question is, so can we like send the missed packet again and again so that we can just
Yes. So
improve the
what we
missed?
do is we know which address the miss packet is from,
Mm-hmm.
right? So it's all about the flash memory address, right? So the way we send a command is, hey, give me the file that's located in this address. That's how we send a command. And then it gives us the data. And then once we get the data and then we look, we see that packet is lost. Then we know which address that packet is lost. And then we command it. But these days, that seems to be a little tedious work. That's a lot of manual work. So what we do is we download everything 50 packet at a time these days. So
Mm-hmm.
we just download 50 packets every time. Set. And we increase the address by 50 packets every time. Right? So we can do that automatically using the ground station software. And what we notice is there is some packets lost in the 50 packet, like let's say 3 packets lost or 5 packet loss, right? That's 10%. We just download the 50 packets again. We don't bother to just target. We just say, hey, give me that 50 packet again. Did that make sense?
Yeah, that answers my question. So
Okay.
I think we don't have any question from the audience anymore. So
So I
we're
have one
okay.
question. So while designing a board, how do we select a proper low dropout regulator? I mean, what things are needed to be considered?
So my way of doing it is especially with LDOs, I would say that it's better if you are starting out to look at what other people have used. So look at the BOMs. I would not suggest you to like find LDO by yourself. Like look at, let's say, go to a website and find LDOs and let's say 3.3 volts or whatever, right? It's better to use what other people have used before, right? And number one, the advantage of using that is number one, it's already tested in space, no problem. So you don't have to worry about whether this will work or not or whatever. Second, you get schematics for that. So if you request that satellite team for the schematic, they will send it to you because they just know that you're trying to not use it for, let's say, economic purpose. You're just doing it for educational purpose. So there is a website. I think it's a QTech database website where all the components that we use is being stored there. Okay, so let's say we used an LDO before. That means it has gone to space. It has worked there. So you can use that data and information to use it. I wouldn't recommend you to just start searching for it itself. You see my point? It's more empirically based than theory based. Uh, I
So
think
is it
that's the engineering process. So if you're really doing science, yeah, if you're doing research about which LDO is good or not, then you can select 100 LDOs and then check one by one. But if you're doing engineering, the most important part of CubeSat is time. To reduce time, you just use what is being used.
okay?
So, and have you looked into the new Raspberry Pi camera that they released recently? The 13, I think, 13 megapixel camera.
We have looked at Raspberry Pi cameras because right now we are using Raspberry Pis as well because it's quite useful. to be working on an operating system, because now once you have an operating system, you have all these other softwares that you can use. But unfortunately, those 13 megapixel cameras are not, let's say, useful for our current purpose. Maybe in the future could be useful. But let's say you want to use that new sensor, right? You have to go through the radiation process. There's no other way. Un- um, Initially, I did recommend not to use the radiation, but if it's completely new sensor that they used, or if it's a new module, you just never know. And unless somebody else has used it before, you don't have to go through the radiation process. If they have not used it, probably better. But if it's a pico satellite, or let's say a nano satellite, that's only 1 or 2 years, maybe you can make an argument. If somebody says do a radiation testing, you can make an argument saying maybe it's not necessary. But in that case, I would still recommend, because it's a new module.
Okay, so we have one more question from the audience. It's from Rajiv Rasali. So he wrote, Mr. Maskey said that the camera system needs to be tested for a long duration to ensure that it works 100% in the real life implementation. So how long is the long enough, and when do you know that the system is okay for the real world implementation?
Yeah, so that's a really good question. How long is long enough? So what we have done is tested it for a month. That's still not good enough if you're really thinking about space, because let's say you're sending up to space for 2 years. 1 month seems to be a small amount of time, but it still gives you a good idea whether your software is stable or not. So what was the second question? What is the other question?
Like, it's the same question.
Okay,
The
so same question,
question
right?
is,
Right. So basically,
oh, okay,
yeah,
so and when do
yeah.
you know the system is okay for real world implementation? I think it's the same.
Right. So the way you would know it's okay is if the software is stable. So you think that the camera will do this when you send certain command, right? You think. But sometimes what will happen is that it does something very different, and it's very difficult to explain why. Like, you just don't know why it does that. Even if you're writing it in the software, like you have specifically coded it. But then you find other ways to recode that and make sure that it works, and then you run it again for a significant amount of time. If it's stable, then you know it's ready. Now, okay, so let's say in CubeSats, you don't have that much time, right? Sometimes you can have only 3 weeks remaining before you submit to the launcher. So that gives you a new problem. So you'll only have to test it with 2 weeks. So you have to be practical at the same time too. You want to test it as long as possible, but if there is no time, you have to run it as much as you can, and then make sure that the software is stable at that moment.
So you mean
So
testing only the software,
previously,
right?
Yeah, software. At the very end flight model, you don't change the hardware at all. If you start changing the hardware in flight model, that means your engineering process is completely wrong,
So,
right?
so my question is like, okay, what about the energy? So, like, are
Okay.
you using any extra sources of energy to charge the
Sure,
battery, or
sure,
using the
sure,
same
sure. You
solar
you have
cell?
to use external source of energy. So in case of our satellites, if you see here, there is a plug that you can plug in, and you can use an external power source to give, instead of the solar panels charging the batteries, right? So what we do is we have a solar simulator. So we don't charge it directly. We charge it in such a way that it goes into a 90-minute orbit.
Ah, okay.
Okay, so 60-minute charging, 30-minute no charging,
Mm.
60-minute charging, and 30-minute no charging. And that's based on the calculation of, because you have 6 sides total. 5 sides is solar panel, right? So you have to see what's the worst case, because not all sides will be lit, right? So the only 1 or 2 sides will be lit. That means, okay, in that case, what is the maximum power you can generate? What is the minimum power you can generate? And then you supply the minimum at that time.
So you
And you
mean
see,
charging it with the minimum current that the satellite will get from the orbit, get in the orbit, right?
yes, yes, that's
So
the
we have
point.
one more question. Does this software performance vary with the environmental condition in space?
Okay, so software, soft, the unless the hardware changes, the software does. I mean, unless the hardware changes, the performance does change. But if the software is not changing, you should not expect the hardware to behave in a different way. Okay, so what we have seen is so far everything that we have loaded and the software to do it has been doing it. Okay, so there is no problem unless the hardware changes drastically. That means the software probably can't run. So either it's 0 or 1. So either it will run properly or it will not run.
I think we have come to an end, I guess. So it's almost 1 hour that we started
All right.
our stream. So thank you for such a technical presentation. So it was really good.
All right.
Yeah.
Thank you
So
very much.
thank you. Thank you for joining us. Thank you for
All right.
giving us your time.
All right.